One of humanity's big questions is, how does a DC motor start running? So let's start with applying some basic physics, and that's the subject of this video. First, we're going to define some parameters, and we start off with the magnetic flux phi. And the magnetic flux is a measure of the number of included magnetic field lines in a coil over here. So B, the arrows B are the magnetic field lines, and the more magnetic field lines the coil includes, the greater the magnetic flux within the coil will be. But only the field lines which are perpendicular to the surface of the coil will be taken into account. The unit of magnetic flux is Weber. Now let's have a look to this picture, and in this picture the magnetic field lines are entering the coil with an angle alpha to this axis, and that axis is perpendicular to the surface of the coil. So only this part of the vector B is part of the flux. So that is Bn, and Bn is B times the cosine of alpha. Now we can define the flux, which is equal to Bn times A. So Bn times A is equal to B times the cosine of alpha times the surface of the coil A. So the flux is B times A times the cosine of alpha. That's the magnetic flux. Now let's look to another parameter, which is the Lorentz force. Suppose we have an electric conductor over here, and through that conductor a current is flowing in this direction. And the conductor is in a magnetic field B, and due to this fact that a current carrying conductor is within a magnetic field, a force will be applied to that conductor, a force which we call the Lorentz force, into that direction. And the direction of that force can be established by using the right hand rule, also called the FBI rule. And due to that rule, we place the current in the direction of your thumb, the magnetic field B in the direction of your index finger, and then your middle finger points out the direction of the force. And when we apply that into this picture, then we see that the force is in this direction. Due to that Lorentz force, we can check out why the motor starts running. Now let's have a situation in which we have a winding over here connected to a DC voltage, and due to the DC voltage source a current is flowing into this direction, and that winding is placed in a magnetic field. We see North Pole and the South Pole. So we have magnetic field lines into this direction, and due to that magnetic field and due to that current, a Lorentz force is applied to this winding, and this is my rotation axis. So due to that magnetic field and that current, a Lorentz force on this part of the winding is into the down direction, and on this part of the winding into the up direction. So the direction of rotation of the winding will be clockwise, so to the right direction with respect to this rotation axis. When this Lorentz force is applied to the winding, a torque is established, and that torque is equal to the Lorentz force times the arm over here. So it's FL times B over 2, half the B over here, because this is a rotation axis, so it's FL times B over 2. But due to this Lorentz force, again a torque is introduced, which is also FL times B over 2. So the complete torque, the total torque, is equal to 2 times FL times B over 2, which is FL times B. And note that the Lorentz force can be calculated by B, which is the magnetic field, times I, which is the current flowing in the winding, times the length of the wire L. When we have multiple windings, we have a Lorentz force which is N times B times I times L. So now we know that these windings will start rotating. So what is the complete torque which is established by having multiple windings? It's FL times B, and FL is N times B times I times L. So it's N times B times I times L times B. Notice that L times B, length times width, is equal to the area, the surface of this winding. So again, the torque is N times B times I times A. And B times A is the flux. So the torque is depending on both the flux and the current through the windings. So it is determined by the magnetic field over here and the current through the winding. So this winding will start rotating. And now something else happens, and that is due to Faraday's law. Because if a flux change occurs within a winding, then an electric voltage is generated in that winding. And we call that the induction voltage, which is the derivative of the flux. When we have more than one winding, so for instance n windings, that inductive voltage is n times the derivative of the flux. And this inductive voltage is known as the back EMF voltage. And EMF is the abbreviation for electrical magnetic force, but it is a voltage. So remember that due to the Lorentz force, the motor starts running, windings start to rotate, and an induction voltage is induced in these windings, which is called the back EMF voltage. And these are the basics of the basic physics of a DC motor. Thank you for watching.